Thank you, sir. Our next chairperson of session is Dr. Aarti Shanware ma'am, Head Department of Rajiv Gandhi Biotechnological Department, LIT Nagpur. Having 25 years of teaching experience at UG and PG level, she has 70 research publications in national and international journals, 24 research articles, and 3 books. She had given 55 lectures as a resource person at national and international level, submitted 20 nucleotide sequences to NCBI Gene Bank. She was honored by awards like Best Teacher Award in 2015 and Nari Shakti Puraskar. I request Minal Devlikar ma'am to welcome such an eminent personality by offering floral bouquet. Now, for further proceeding, I am handovering the session to the chairpersons.
Thank you, madam. Dear friends, good afternoon. Today is an important day, you must be knowing that. Anybody guess? Yes, exactly. Today is the World IP Day, Intellectual Property. 26th of April every year. So we are celebrating this IP Day. So I am congratulating all people to assemble and listening this lecture. I welcome all the three eminent speakers. First, Dr. M. Swaminathan. Probably I would like to introduce him. Just I spoke to him. He is also from Tamil Nadu. I am also from Tamil Nadu. So just I spoke to him. Yes, after seeing his experience, I am really excited. So Dr. M. Swaminathan from MSc, he did from Annamalai University 1972. PhD, IIT Kharagpur 1983. So his teaching experience, if you see that it's a 40 years of experience, is going to give you the lecture on eco-friendly nanomaterials for the organic transformations. This would really help you to inspire you to plan your experiments or inspire to take your projects. Then he has the international and the national publications. You can see that H index is 54. Book published is book chapter published 9. One book is published. Research guided PhD 20 students. There are many things, research interest, other things. It is going on the big list. So award also many awards he got. So probably it's I would tell some of the awards. So Tamil Nadu Scientist Award 2008, Chemical Science from the Tamil Nadu State Councils for Science and Technology, Government of Tamil Nadu. Silver Medal Award 2005 for research contribution by Indian Association of Solid State Chemistry and Allied Scientists. Bronze Medal Award for 2012 from this research contribution of chemical science by the Chemical Research Society of India. Then Lifetime Achievement Award for the material science in an international conference on futuristic materials held in RTM University, Nagpur during 2015. Like that, there are many awards we can, it goes on time due to the time constraints. So I would like to invite the Professor M. Swaminathan to deliver his lecture. Thank you. I would like to request Dr. Aarti Shanware madam to say a few words.
Good afternoon, everybody, and I then wish you all a very happy IPR day. As sir has rightly told, we have many innovations, at our disposal, but we unfortunately publish it. We don't want going for patenting, so I appeal on this esteemed listeners and participants to go in for patenting before thinking of publication. So, and I'm highly impressed by your CV, sir, and I would like to request you to proceed for your session. Thank you.
Thank you, the chairman, for a nice introduction of conference, and madam, and very good afternoon to all of you. I thank the organizers for giving me an opportunity to present some of our work on that materials that were synthesized, particularly that they are used for some of the organic transformations. And here what you can see, and this is actually our university. I am actually retired from Annamalai University as a chairman of the organic chemistry department. And now, presently, I am working as a visiting faculty in the Kalasalingam Academy of Research and Education. Shortly, this is a deemed university called Kalasalingam University. It's a Trivandrum, you may be knowing that, about 60 kilometers south of Madurai, and it's located in a beautiful environment that all surrounded by mountains. The mountains are called the Podigai Mountains. That is why one express train going from Chennai is called Podigai Express. So this is an excellent location, and there we have an international research center which houses 4 laboratories. All the 4 laboratories are dedicated to materials: biocomposite material laboratory, multifunctional laboratory, and nanomaterial laboratory, and all. So in the nanomaterial laboratory, I am working as a visiting faculty. Once in a month, we go there. I have some students, particularly some PDFs, and they are working. In the development of some of the materials, particularly the catalyst, photocatalyst, solar active photocatalyst, and using them for the multiple applications. So this time I wanted to take up these materials used for the organic transformations. Though we had worked with the organic transformations long back, some 2 of my students had got PhD only in that, working in the organic transformations, maybe some 15 years back. Again, we want to take up that one, so that's why I've taken this subject. And our work is only a past one. And presently, I would like to say something about this the photocatalyst, which can be used for some of the organic transformations, most of the organic transformations. Then I'll go to some of the catalysts that we synthesized and how we use them for the organic transformations. So you can see that, and as far as I know, everybody knows that nanomaterials, particularly the European nanomaterials, photocatalysts, and they are being used for that organic synthesis or organic transformations. Actually, this subject came to my mind only induced by my student, and we were working in the environmental remediation, and that student wanted to only in organic synthesis. I told him, okay, you use the photocatalyst and do the organic synthesis. He started doing that, so that we are exposed to that field only at that time, maybe in 2006 or 2007, during that time. So here, you know that everybody knows that green revolution in agriculture, long back it came, and then 1970s the green technology in the industries came to the existence. And what is that green technology? For the green technology, what we require is a green chemistry experience. Because as you told that academically we have to find something R&D, then only it can go for the technology. So the green chemistry and principles everybody knows about it. So the green chemistry, basically one of the green chemistry is the use of the catalyst. So we all of us know that catalyst is a tremendous opportunity to improve environment as a process can produce a cleaner and greener technologies. So catalysts are the first nanomaterials with wide application both in academic research and industry. And present requirement is, as now everybody talked in the morning, we have to develop the new materials, because no material, no progress. That is its saying. So we have to develop the new materials, particularly, eco-friendly materials to catalyze for multiple applications. This is again to catalyze organic reactions, but generally for the multiple applications. So developing high performance novel materials with the right and conditions are gaining much importance in the recent year. And among the catalysts, the photocatalysts play a vital role because photocatalysts can make use of solar energy. The solar energy utilization is also there. So what we are going to see is some of the organic transformation by the photocatalysts and some of the organic transformation which can be induced by the catalysts, which are solid acid catalysts. So basic principle everybody knows as a photocatalyst, semiconductors. Most of semiconductors are used as a photocatalyst. So the photocatalyst, when you irradiate the photocatalyst, an electron from the valency bond goes to the conduction band. So we have an electron in the conduction band, and a hole is created, or a positive charge is created in the valency bond. So we have two species. One is a hole, another one is an electron. So here the electron can react with oxygen forming superoxide radicals which can completely oxidize the pollutants. Similarly, if you take the hole, it can react with OH minus ion or water molecule, producing the hydroxy radical which can completely degrade or oxidize the pollutants. So this is the principle involved in the degradation. I mean, how it can be used, semiconductor can be used as a photocatalyst in the degradation of the, pollutants. And another one is, this is another application is, when we have an electron and a hole, electron can be used for the reduction. All of us know addition of electron is a reduction. And coal can be used for the oxidation. So the beauty of this semiconductor or the photocatalyst is it can be used as a unique catalyst, a redox catalyst, both for oxidation as well as for the reductions. And that is why you can see that electron can be used for the reduction and the coal can be used for the oxidation. Suppose you have a molecule, two molecules, one molecule you can oxidize, another molecule you can reduce, they can combine together to form a third molecule. Three stages can be used, performed at one experiment by using one catalyst, that is a redox catalyst, a photocatalyst. That we have done some experiment like that one. So this is something like advantages of this semiconductor photocatalyst. All of us know this is not toxic, inexpensive, and it can be used without loss of activity. Particularly, this is most important is the reusability of this one, because the catalyst can be reusable. Most of the catalysts are reusable. That is most important. And another one is that what we require is only either UV light or solar light. But normally we avoid using the UV light. We are developing only solar active photocatalyst so that we can make use of either visible light or solar light. Nowadays even LED light. So more selective than the photochemical reactions. Everybody knows when you take an acetone and irradiate it, you get a number of products. So they are not selective. Whereas photocatalytic reactions are more selective. So you can use it for a specific purpose. If you take an alcohol, you can use a photocatalyst to form up to the aldehyde stage. So that is why they are more selective than the photochemical reactions. So what we are going to see is some of these reactions. Some examples is only taken from the literature. The nanomaterial can be used as a catalyst for oxidation or oxidative reduction, substitution and combined redox reaction. So this is a direct oxygenation. So they are used only TaO2 with the acetonitrile solvent, and they are getting this ketone. That is, this formation of this ketone. That is oxidation reaction. And similarly, you can have deoxidation reactions or sulfide to sulfoxide to sulfides or nitrones to alumines. You can see that these nitrones to forming the alumines, and similarly sulfoxide is forming sulfur SO, and SO is forming the sulfides. So all these deoxidation reactions. And similarly, TaO2 can be used for the fluorination of this one. So by in the presence of silver fluoride and the TaO2, you can get a fluorinating that compound. So you can see fluorination or fluoroalkylations. And similarly, the oxidation reactions. You can see the oxidation toluene can be oxidized to benzyl alcohol, trichloroethane or methyl alkyl. Alkanes can be oxidized to the alcohols. See, these are some of the reactions. So this is again oxidation of naphthalene in the aqueous and organic solvents. And you can see that in the presence of TaO2, in the presence of light, if using the TaO2, you can get these different kind of products. And the reduction is more important. Generally, the photocatalyst is mainly used for the oxidation. Suppose in the aqueous solution, if you irradiate a pollutant by using a photocatalyst, it completely oxidized. And whereas if you use it in the non-aqueous solvents, you can have the reactions. So in the case reductions are very rare, but reduction can be done because once you separate the hole, then the electron can be used for the reductions. Otherwise, normally reductions are very, very active or slow. So this nitro can be, reduced to aniline. NO2 can be reduced to aniline. There's so many examples are there. So this is actually nitrones and all these. How this nitrobenzene or oxidation is a different kind of mixture. This is cadmium sulfide. Actually, here this sodium format is used as a, actually is supplying that one, removing that hole so that it can convert it to a carbon dioxide. So the electron can be used for the reduction. and carbon capture and carbon dioxide reduction. This reaction has been already reported. Carbon dioxide can be converted into methane by using the photocatalyst. This is another reaction which is heterocycle functionalization, and this is other reaction. So the reactions which can be used by TiO2 and cadmium sulfide. And this combined reduction, as I told you, that nitro can be reduced, NH2, and alcohol can be oxidized to aldehyde, and they can combine together forming a this one. Combine this reaction. Okay. So these are some of the reactions which have been already reported by using this photocatalyst. And what is the drawback? Simple TiO2 cannot be used because the electron hole recombination is taking place. Another one is that you have to use only the UV light. So charge carrier recombination occurs within a nanosecond, and the banded absorption threshold does not occur the utilization of the visible light. So we have to modify the TiO2. So once you modify the TiO2, once you make the TiO2 as solar active or normal TiO2, you can take zinc oxide or any other photocatalyst silicon oxide which are active in the UV region. You can make it the solar region, visible light region by modifications. So many modifications have been reported every day, and it can be modified by doping with metals or non-metals or metal halides, or you can use anions, or you can use that semiconductor oxide coupling it to another semiconductor oxide, or you can use that surface active materials like fluoride and activated carbon. All these are different procedures which have been used for modifying UV active photocatalyst to the visible active, or to increase the surface area, or to make it more efficient in the photocatalytic activity. So we have done, actually this is 18 tests, we have done more than 100 photocatalysts and tested for environmental remediation. As far as our work is concerned, mainly we use it, initially we test only for environmental remediation. Normally we take a dye and then we test for dye degradation, and then nowadays the pharmaceutical ciprofloxacin or diclofenac and other chemicals, any CEC, emerging contaminants or emerging concern that we are taking, and then we are completely degrading that by using this our photocatalyst that we test for only for environmental remediation. But this catalyst can be used for as a electrocatalyst in supercapacitor applications, and also in that electrocatalyst in the methanol fuel cells, and the antimicrobial activities. So many other applications are there. Multiple applications are there. So this is generally the method used for characterization of material, and this is the one that we prepared in that long back silver doped TiO2. That time when we reported, actually this paper we published at the time, it has got more than 600 citations, because that time we reported silver TiO2 and it was very useful for. We tested only for environmental remediation. Later on, they used, my student, as I told, he used for photocatalytic organic synthesis. So this is actually external factor, and you can see, 0.5% silver loaded TiO2 and 1%, 1.5 and 2. You can see that 1% silver loaded TiO2 is having the maximum absorption to this protein. So initially, whenever you prepare a catalyst to find out whether it is solar active or not, you have to take a TRS spectra and find out whether the absorption is lies in the visible region or not. Then only we can go for solar active applications. So this is actually HRM images, which can give an idea about the particle size distribution, and also presence of the silver and other things and crystallinity, everything is HRM image. So I didn't want to give characterization of all the materials that we prepare. Only one material I have taken is HRM analysis. And first time when we started our work on organic synthesis, this is the one which induced us, which even inspired us, actually, I can say. So this is the work that my student saw in the paper, and he said that, sir, that they are used to that TiO2 and in the acetonitride. Why can't we use our silver TiO2 and other things? Then we use the same reactants we have taken, that is orthopropylene and propylene glycol, and this is already reported by Professor Subbarao and Subramanian in PhD letters, but the yield was very low, 22.5%, and only 12.5% of this 2-methylphenylene, phenoxylene, and orthopropylene diamine. Then we have taken the same in a reactants, and we used our silver TiO2 with 5% clay, because they have used that another material, zeolite material. Instead of that, we used 5% clay with silver TiO2. We found that different products we obtained. You can see that silver TiO2 with the clay 5%. We receive, we obtained the products 2-methyl benzimidazole and benzimidazole. That too, the conversion was 90%. And with orthogonadamine, with the different alcohols also we tried, we are getting the different kind of alcohols. So this one we got it immediately. We have sent the paper to the same chemistry letters, they published it immediately. So that was a very, good inspiration for us at that time. And then he has taken about more than 30 to 40 compounds and prepared it. That is it. So then we prepared. This is the one which is actually comparing with the different, percentage of clay and other things. We found that optimum is 5% clay. With the solar light and both solar light and the UV light, you can see the percentage is 92% conversion and 78% conversion. And we also compared with the other materials. We found that silver TiO2 is found to be most efficient. And then later we prepared that platinum TiO2, palladium TiO2, and the gold TiO2 and all these things. All are very good. And more or less, except palladium TiO2, all are more or less equally efficient. And this is the one which I told you that initially that the student after testing with a simple reactant with orthogonadamine and propylene glycol, he has taken with so many substitute orthogonadamines and so many different glycols and alcohol, and he has done more than 30 compounds. So another one is that the redox reaction which I was telling that it can be used as a redox catalyst both for oxidation as well as for the reduction. So we have taken a nitrobenzene and alcohol. Nitrobenzene is reduced to aniline and alcohol is oxidized to aldehyde, and they combine together forming the quinolidine. So this was actually a combined redox reaction. This redox catalyst and multi-step synthesis. Is only one step we are performing all the three. So you can see that this was actually very good, and he has taken nitrobenzene and substitute nitrobenzene, and we are able to get a very good conversion efficiency. And similarly, it's not that nitrobenzene, we can also take that aniline directly and then with the alcohol, and the same that we are getting. And here the nitrobenzene with the platinum TiO2, the same reaction performed with the platinum TiO2. And here this actually nitrodiphenylamines have been taken to the platinum TiO2, and they also prepared this with the platinum TiO2 and performed the experiment with solar. And this one actually was reported in the artificial synthesis about our the redox catalyst at the time. This is nitrogen. You can see that nitrogen TiO2, the absorption in the viscous region increasing when compared to the prepared TiO2. And here again, we are compared with different substitute nitrobenzenes. You can see that how this nitrogen TiO2 is very effective in comparing this reactions. And finally, we compared with all the things in the same nitrobenzene forming the quinolidine reaction. Silver TiO2, AgTiO2, AuTiO2, NTiO2. You can see that UV light and as well as the visible light. And nitrogen TiO2 is found to be very good in the visible light. And another reaction that we have performed is a deoxidation. That is that NOH is removed and then substituted by oxygen. So benzophenone oxygen is taken. The deoxidation reaction was done with this one, and with the different catalysts we have performed that one. And the percentage of conversion is given here, effect of the various catalysts. And you can see the silver TiO2 is very efficient when compared to the other catalysts. Similarly, we have taken other solvents. In all the solvents, mostly we have taken organic solvents, and organic solvents you can see the isocyclic dichloromethane is the best one, and then acetate. And different oxygens we have taken, and then the same reaction was performed with the TiO2 P25 is nothing but the mixture of two rutile and anatase, 80% anatase and 20% rutile. Okay. So that's all about the work on the photocatalysis. And the same catalyst can be used as a solid acid catalyst. Actually, one time that we prepared that initially a sulfated TaO2. A simple, by using sulfuric acid, while during the preparation of TaO2 itself, we added sulfuric acid and we prepared sulfate TaO2 reported that time. It was, we are prepared only for that degradation of the, pollutants, but later we found that the catalyst can be can be well used for these organic transformations, particularly as solid acid catalyst. Because instead of using the solid acid catalysts are very, very advantageous because they can be separated and they can be reused. So, sulfate loading sulfuric acid increases the sulfuric acid TaO2, and this catalyst is excellent yield with less reaction time and expensive or inexpensive and recyclable catalyst. So you can see that condensation reaction by using the sulfate just by stirring it at room temperature with 3.51 of ethanol, sulfate TaO2 immediately you can get 100%, nearly 100% conversion of this compound. Similarly, condensation of 1 diamine with benzene, all the reactions are have been performed. We found that the catalyst is very, very, very useful and excellent. And that time we reported first time, and then later on, recently also we had a review on sulfate TaO2, not myself. Somebody has written the review, and they have reported all the reactions are being referred to this one. And here the advantage is this solvent catalyst can be used in the water also. You can see the efficiency at different solvents. Even in water, it is having a 97.3% efficiency, yield. And this N-formylation reaction in N-formal compounds are, industrially very important. The formylation reactions, because the N-formal compounds are being used in the industry as a, for so many applications. So these N-formal reactions, whether it is a primary amine or secondary amine, can be formulated by using the formic acid and acetonitrile. Either you can use TaO2 P25 or TaO2 sulfate TaO2, but sulfate TaO2 is found to be more efficient and also recyclable. Whereas TaO2 P25 is not recyclable. You can see that just 30 to 49 minutes stirring at room temperature can give 99% conversion of N-phenyl formaldehyde. And this, paper at that time it was a top secret paper in the molecular catalysis. So you can see that efficiency, even after 5 runs, same catalysts were reused, filtered and dried and reused. You can see that 98.3% efficiency even at the 5th run. And this is another reaction by using the same solid as catalyst, sulfate TaO2, a condensation reaction. And this is again another reaction that is a, cyclization reaction by using the primary amine. Just like room temperature grinding. And this is actually multi-component reaction can be performed. It is not mine. In some other lab, they perform the reactions by using these, various substitute aldehydes, aromatic amines, and ketone esters by using 5% of TaO2 sulfate as a catalyst, and they are able to get this derivative, that is functionalized piperidine derivatives are being prepared. So many compounds they are prepared and reported. And this is another one which is also used as solid as catalyst by acetophenone is forming diptone, and this is going to be very good reaction by using the same catalyst. So these are some of these reactions which have been performed with sulfate TaO2, and sulfate TaO2 now recently we have started preparing the modification of sulfate TaO2 because sulfate TaO2 is found to be efficient, and now we are prepared. Actually, tomorrow that one presentation is there by my student. He is presenting. He is going to present maybe today or tomorrow sulfate TaO2 with hydroxyapatite. Professor Adhikari was telling about the performance of hydroxyapatite, and it is a very good support material. So the hydroxyapatite supported sulfate TaO2 prepared it, and then we are used again. Normally we test only for environmental remediation for degradation of toxic chemicals, but that can be used for the organic transformations. Not only for organic transformations, I feel it can also be used for the water splitting because TaO2 already reported. In 1972 itself, Shishima reported TaO2 for water splitting. This is a modified TaO2 only. So even it can be used for the water splitting, maybe for the hydrogen production. So many applications may be there. So we have prepared a sulfate TaO2. We have actually modified sulfate TaO2 by the hydroxyapatite and also by C3N4, graphite carbon nitride, and also some metals we have used so many biochar and all these modifications we are doing it, and the progress is going on, because sulfate TiO2 is one of the versatile material. I feel that acidity, we have tested the acidity of the sulfate TiO2, both Lewis acidity as well as the Brodson acidity. We have measured, I didn't have the values, but it's a very acidic, very good acidic catalyst, and can be used as acidic, the solid acid catalyst, or it can be used for other purposes also. So these are some of the students who worked with the solid acid, sulfate TiO2 long time. That Selvam, and they are all now well settled, and all of them they have done only the synthesis. Synthesis work by using the solid acid catalyst, sulfated TiO2. So I thank these students who have done the work on sulfate TiO2. And presently, as I told you, a present student is, because I'm not guiding any scholars for PhD. I am only a PDF student, and they are working on that modification of the TiO2, sulfate TiO2 with HAP, C3N4 and other materials, and they are preparing, and those things, those catalysts can be used for their several applications. Particularly, we want to use it for organic transformations, because already it's reported for organic transformations. Maybe that may be more efficient, and organic transformation and other purposes we will use it. And the applications are being, the progress is going on. And I thank our university, Annamala University and Kalasalim University Education. And we had a project in the Ministry of Environment, CSDR, and all these things. Thank you very much. UGC. Thank you. This is our I am from Chidambaram. So where the Raja temple is there, it's a small town. This is a temple town. So the Chidambaram is well known for the Raja temple. So one side Raja temple, another side is university. There are two temples. This is temple of God and temple of education is there. So we have, it's a very good place to visit also. Thank you very much for you.
Excellent, sir. Excellent presentation. Of course, Nataraj Bharatanatyam, whoever knows the Bharatanatyam knows that Chidambar Nataraj statue. So that place. Thank you, sir. It's excellent presentation. Moreover, it's applied aspects of the nanotechnology, and it's going to solve many pursued problems. The session is open for the discussion. If you have any specific question, please you can go now. One or two questions, please, quickly. Anybody? No? Yes, sir.
Sir, what is the possibility of utilizing polymers, natural polymers, as the support to this kind of reactor?
So this sulfate they are only support with the biochar and as well as the redox chemical. We have not tested for the applications, but we have prepared the catalyst and tested for the degradation purpose. For degradation purpose, but we feel that it can be well used for the organic transformation. So that we have to do it and support materials can be used. That again we are going for this these C3 and gravity carbonate, and as well as this graphene oxide, RGO, all these things.
Any more questions? Sir, I have one query. What about the biosafety of the nanomaterials using in the field? Biosafety.
Support materials, there is no problem of toxicity because we can easily separate it and then reuse. When we don't use that support material, the separation as it goes in the morning, some of the separation may be difficult and all this. Either to be magnetic or to have support. So mostly now we go for support material. Nano-composite. Most of them nowadays that we prefer only nano-composite. So nanoparticles better to prefer the nano-composites so that it can be separated and taken. So nano-composite means one is the nanomaterial, another one is the bulk material. Otherwise, there is something, not there.
Yeah. Because we have one our research organization at Mumbai, CIRCOT, that is they deal with the cloths, mainly the manufacturing cloth. So what they do that nanoparticles, they coated that especially the hospitals, the bed sheet and all, they are quoting that that is a patented technology, of course. They patented one so that it won't bed blood and the stain, it won't stick on to that. It's a completely safety for the patient.
Now also we have a paper on the nanometer code from the paper, nanometer code on the cotton papers, and nanometer film inspirations.
Yeah. Thank you, sir. Excellent lecture. Thank you. Now I request our co-chairman to introduce the second speaker. Thank you, sir.
Thank you, Dr. Balsubramanian. I'm happy to introduce Dr. Naveen Chandra Shimpi sir. He's professor right now and from Department of Chemistry, University of Mumbai. His first area of research are nanomaterials and their functionalization, biodegradable polymers and rubber nanocomposites, materials for gas sensing, nanomaterials for effective degradation of dyes, and synthesis of nanofibers. The research field which is very near to my heart also, and some binary materials. Is life member of Asian Polymer Association and Indian Science Congress. He has many research publications to her credit. He has about 95 international and 2 national publications, and he has presented more than 100 papers in various national and international conferences. He has particularly on today's backdrop, I would like to share that he has 3 patents granted and 1 filing process, which is under examination. He has 1 book published, 2 books, sorry, and he is editorial board member of various national and international journals, the Open Material Science Journal, Nanoscience and Nanotechnology Asia, to name a few. I am very happy to have you, sir, over here. It's interesting you to kindly proceed. Thank you.
Excuse me, ma'am. Just before we start this invited talk, I would like to offer bouquet and felicitation of Mr. Swaminathan, sir. I request G. Balsubramani, sir, to felicitate Swaminathan, sir, by offering memento and certificate. Thank you, sir. Yes, now I request Shimpi, sir, continue with your invited talk.
So good afternoon, one and all. Before to proceed with my talk, I thanks to the organizers of ASFM-2024 for inviting me to deliver the talk in this well-known conference, that is Materials for Sustainable in Chemical Sciences, Biological Sciences and Physical Sciences. I thanks to my very good friend, Professor W.V. Gurnole and Professor Babai, principal of the college, for inviting me in this particular conference. My topic is particularly based on advancement in the materials. So therefore, I named this particular lecture on advancement in gas sensing to heterogeneous catalysis from zinc oxide nanostructure to hybrid materials. There will be the 2 aspects. One is for the materials can be used for the purpose of the sensing of gas, means for the development of the gas sensor. And second aspect is for the organic transformation reaction and as well as for the water treatment. Therefore, I named it as a heterogeneous catalysis. When we talk about the materials are basically in the form of the solid. And when we talk about the material is having a specific size. that is ranging from the micron size to the nano size. Before 2 years, 2 decades, material scientists uses materials of micron size. But when they are using these materials for the advancement or for the applications, like various field of application we talk, that is from the paint industries to pharmaceutical industries, the pharmaceutical industry to rubber industry, and many more in the construction industry. What they find that because of the addition of the micron size material, here is the disadvantage. What disadvantage? We get the properties, better properties for the material, but the amount required for the improvement in the properties is very high. And therefore they come to the conclusion that we need such a material which can enhance the property in a very smaller quantity. And therefore the nanotechnology comes into existence. Actually, this technology was from the ancient time, but people doesn't know about the size of the material. They are using that material. That is why the Bhasma is in the form of the nano. And that in ancient time, these materials can be used for the wound healing and many applications. Why we turn up into micron to nano? First thing is the surface to the volume ratio. There is the increase in the surface to the volume ratio. And when we talk about the micron size, there is the decrease in the surface to the volume ratio. Means maximum amount is required to cover the large surface. Here, minimum amount is required to cover the large surface. Means when we talk about in terms of the paint, the hiding power is getting improved in a smaller amount. And this is one aspect, that is the size. Second one is the morphology, that is the geometry is one part. And third one is the porosity. If material is highly porous, means when we talk about the catalysis, a heterogeneous catalysis, material should have all these high class properties, that is surface to the volume ratio should be high. Second one is the geometry, and third one is the porosity. If material is highly porous, then the removal of the impurity from the surfaces becomes very easy, and therefore these things can be highly important. In terms of the gas sensing, porosity is one of the important ones. And when we talk about the nano, like everyone says 1 nanometer to the range of 10 to minus 9 meter, 10 to the power minus 9 meter. That is not the limitation. That is, at least one dimension should be in the range of 1 to 100 nanometer. When we talk about the line, when we talk about the dimension, in that case, length, width, and height is given there. And therefore, in terms of the dimension, nanometers comes from 0, 1, D, 2D, 3D. When we talk 0D, length, breadth, and height are confined at a single point. And simultaneously, the dimension is affecting on that particular in terms of the length, breadth, and height. When material converted into the smaller size, all these properties are getting changed. Melting point is getting affecting, boiling point is getting affecting, optical properties are changing, electrical properties are. Means heterogeneous catalysis or a gas sensing material can be implemented in two classes. One is on the basis of polymer supported, and second one is a simple nanomaterial that can be utilized at a room temperature. And when we talk about the polymer supported, that can be utilized for the higher temperature. Means in terms of the aspects of the safety purpose, that motivation can be solved because of the polymer supported. This is the general side about the nanotechnology. As I mentioned, that is the dimensions 0D, 1D, 2D, and 3D. The properties of the material can be defined at the nanoscale because of the two reasons. That is, I mentioned that surface to the volume ratio, chemically reactive. Third one is the quantum confined. Materials are confined at a single point. That is a quantum confinement. And when we say surface to the volume ratio increasing, smaller size is getting increasing, material becomes lighter in weight. Therefore, gravitational forces become negligible, and electrostatic forces are get dominant. When gravitational force become negligible, electrostatic forces are get dominant. That time means that a wave dispersed material can be agglomerated after 2 times or sometimes, and therefore the stabilization is required. And when to balance the electrostatic forces of attraction, we need to modify the surface of the nanomaterial so that de-agglomerated system can be possible, and de-agglomerated material can improve the properties as per our expectation. So when we talk about the sensing, these are the application of the gas sensor. Detect combustible, flammable, and toxic gases. Detect industrial leakages, whatever the leakages are there, gases, a small amount of the leakage that is in the ppm level, that can also be possible with the help of these gas sensors. For the environmental monitoring, human health care, that is for the detection of our, when a person drugs anything, the alcohol detection can be possible at the very smaller level. For the home safety, why this gas sensor? Highly efficient material, very cost effective. If we select a very simple and a very cheaper material, then that sensor becomes a very cost effective, very compact, very smaller sensor. We can carry that sensor very easily as like a pen drive, and 30 billion of the industries utilizes right now these types of the sensor. When we talk about the present sensor, need to be operated at high temperature. That is at room temperature as well as high temperature that material can utilize. Increasing the power consumption, poor selectivity, stability, selectivity at low concentration of the gas, and shorter lifetime. Means micro technology to nanotechnology. I compared till time what is micro technology and what is nanotechnology, and why we need to go towards the nanotechnology. Advantages of quantum properties of material for the ultra sensitivity. These are the sensors: cheapest micro gas chromatographer, rad size measuring instrument, and hydrogen sensor using palladium nanoparticles. This is the difference. How the miniaturization of the technology is going to happen. That is I want to focus here. These are the few photos. These are not the photos we have in our laboratory. We have developed this type of the sensor in a compact manner, and we are trying to put this type of the sensor for the selectivity as well as for the time being, means how much reusability is possible for this particular sensor that we have tested. So here, zinc oxide, versatile material, conducting polymer we have used, that is a aniline we have been taken here as a supporting material because of the high temperature response for that particular sensor. Polymer, then we decorate this particular material over the surface of the polymer, and we call it as a polymer metal oxide hybrid materials. Therefore, the material is from zinc oxide to the hybrid material. That is why we have mentioned it. So synthesis here, in situ oxidative polymerization technique was used for the penny. Whatever the penny we have synthesized, that penny also in the form of the nano size, and then we dope nickel dope zinc oxide. We here use the word scientific, that is a doping, but actually it is not the doping, it is a decoration. Means over the surface of the zinc oxide, we have decorated this nickel material over that particular surface, and therefore it is called as a nickel dope zinc oxide penny hybrid gas sensor. So here the XRD ranging, that is amount of loading of nickel is ranging from 2%, 5%, 10%, and 15%. And further, we have utilized zinc oxide, nickel dope zinc oxide, penny, simple penny we have done, and zinc oxide penny and nickel dope zinc oxide penny. Means how many categories are there? That is a doping percent we have varied. With reference to doping percent, we have compared the material with the pure, that is a virgin material, that is a pristine material, that is a zinc oxide as well as a penny, and that penny is doped with pure zinc oxide, and penny is that is nickel doped zinc oxide over penny, like this. These three categories, 3 to 4 categories we have done, and accordingly the ratio, average crystallized size and unit cell volume we have tested. So this is FTIR, that is we have been verified the material, whether it is the formation of the material is not done, is done or not done. That is, if you look into the values, that is 1722 to 1196, that is for the polymeric material, that is from 2878, and the rest of the values which is below 500, that is for the zinc oxide and nickel. Then we have done with UV DRS, that is DRS for the solid material. Therefore, DRS diffuse reflectance UV spectroscopy we have used, and then we have tested its thermal stability also. The values are being put here in the table. Weight loss in percent, that is a initial decomposition temperature, mid decomposition temperature, and final decomposition temperature. Initial decomposition and the final decomposition, that is these two temperatures are very important. Means initially material starts to decompose, initiation is there, and final means material is completely decomposed. That is there is a formation of the ash content. And when a material takes more time for the decomposition, that material is said to be or supposed to be considered to be as a thermally more stable. So this is the morphological study, that is a field emission and transmission electron microscopy we have done. If we look into the diffraction pattern, it seems to be a polycrystalline material, and over the surface of the rod, zinc oxide shows a rod-shaped morphology, and over that particular surface of the rod, there is a decoration of nickel over the surface of the zinc oxide. Doping and surface analysis with the help of the XPS, that is a 01S, 1C for the carbon, and the rest of that showing the convoluted and deconvoluted spectra. With reference to this, the change in the binding energy will happen, and we observe that that is a nickel dope zinc oxide tanning shows very effective convoluted and deconvoluted spectra. That is the state of the oxidation of that particular material. Here is the gas sensing setup we have used. It is a completely computerized base, that is a Ketley electrometer in your hand. Then the gas sensing dome is there. If you look into that, searing is having the gas saturated solution for the testing of the material for different humidity ranges from both sides, and temperature controller is there. We have the temperature controller, and we have also the setup in such a way that we can test the material at different humidity ranges, that is from 11% to up to 84%. 84% means in Mumbai we don't have the problem of the humidity, because in a normal condition the humidity is always been more than 70%, and in rainy season it goes up more than 80%. But we didn't have the chance to get the humidity less than 50% or less than 60%. Therefore, we have to set up this particular humidity control by using the solution, and therefore saturated solution we have to use. So this is the gas sensing for this particular material. What is the sensing? When we start to pass the gas, initially when the gas is in, that time there is an increase in the resistance, and when we reach to the level of saturation, means once the material reaches to the saturation, the resistance seems to be a constant, and as we start to degassing, the resistance goes on decreasing. Means gas is in, resistance is increasing. When gas is saturation level reaches, the level of the resistance is constant, and when gas is out, the resistance goes on decreasing. So there is the conversion in the, as previous speaker told about the valence to the conduction band and conduction to the valence, there is the electrons and the hole, and finally the recombination is there. Means initially the oxidation and then goes with the reduction. That is the process. The change in the conduction to the valence band to the conduction band, that difference increasing, it shows that the material is working as a good sensor, and it degasses the gases in a uniform way. So sensor response, when we talk about the sensor response, 75% of the response is being observed. 82 Response time is 82 seconds and recovery time is 399 seconds. Next, we have done that is we have synthesized 1D tin decorated spherical shape zinc oxide. As I mentioned, 0 dimension, 1 dimension, 2 dimension, and 3 dimension. In that, we utilize tin as a 1-dimensional material. Again, zinc oxide. Synthesis of tin doped zinc oxide by using 3 methods. That is, one is a co-precipitation method. We have used zinc acetate plus tin acetate, which turn the solution to maintain the pH and to precipitize that particular material. That is, ammonium hydroxide is being used. Turbidity is formed. We filter the compound, dry it at 70 degrees centigrade for 10 hours. Then go for the calcination in a crucible in a hot air oven at 500 degrees centigrade. That gives the tin doped zinc oxide. Second method we have adapted, that is a hydrothermal method. The same process, instead of co-precipitation, direct co-precipitation, we put that entire solution into the autoclave, because temperature control can be possible as well as pressure control can be possible. In a co-precipitation, temperature control cannot be possible or pressure cannot be. It is atmospheric pressure. Okay, so one is a hydrothermal method, second one is Soldier method, and upon comparing all these, we found that hydrothermal method is the best method for the tin doped zinc oxide. These are the excited patterns of tin doped zinc oxide. Acid peak is observed at 112 and zinc oxide peak are observed at 100,002 and up to 201. Means the combination of extra peak, formation of the extra peak suggesting that doping is been happened. We have done the FTIR and UV visible. If you look into 5% tin doped zinc oxide, the absorbance goes up to 376, and for pure zinc oxide, it goes to 364. This is the FEACM, uniform and a very scattered form of that tin doped zinc oxide is been observed. This is the high resolution TAME and SAED pattern for this particular material, polycrystalline. This is the elemental decomposition study, presence of SN, zinc, and oxygen. XPS we have done. 01S peak observed at 529, that is binding energy is 529.87 electron volt. For zinc, it is 2 peak, that is of orbital form. SN also at 2 peak. And this is the study we have done. That is a different percent of SN doped zinc oxide and their response time. It has been observed that 5% of SN doped zinc oxide shows very good response. Effect of concentration, if you look, that is at 5 and from 10 ppm to 200 ppm we have tested. Here is the gas in response 30.9 second and 63.54. Response time 30.90 second, recovery time 63.54, and overall the sensor response is 75%. Effect of humidity we have tested, as I mentioned that sensor should be operate at various humidities along with the stability study. So here we have done the comparative study with other material, that is the SN zinc oxide, and our study is the 1D zinc tin decorated zinc oxide shows we have tested for the acetone. We have done the selectivity study also, and in the selectivity study we observed that it responds very effectively for the acetone at working temperature 150 degrees centigrade, concentration 100 ppm, response time 30.19 seconds, recovery time is 63.54, and the stability of sensor is for 6 days. Another is copper doped zinc oxide nanostructure for the acetyl air gas sensing. These are the excited for copper doped zinc oxide. Again, if you look into this, copper shows 2 additional peaks, that is 311 and 400. In the combination of with doping from 3%, 6%, and 9 to 12%, the additional 2 peaks are being observed compared to pure zinc oxide. FTIR of copper to zinc oxide, that is zinc oxide, zinc and oxygen bond appears at 898 centimeter inverse, whereas zinc oxygen bond that is for because maybe the impurity is there and there is a hydroxyl group at 3488 centimeter. This is a UV visible spectra. If you look into this, the absorbance is getting changed. That is from 364 to 401 nano. This is the morphology study. Uniform and dispersed form of the material is being observed with uniform size and dispersed. This is the HRTM. This is X-phase of copper to zinc oxide. Zinc at 2 ppx shows binding energy that is 1021.11 to 1044.82 electron volt. Oxygen 1 is fixed at 529.87 electron volt, and while for copper 2 pp 933.24 to 955.38 electron volt. We have tested this gas sensor for the acetaldehyde. If we look into this, we have taken for the zinc oxide as well as for the doping of the copper. In this, 9% of copper doped zinc oxide shows base sensing response at 100 degrees centigrade. We have gone up to 200 degrees. Then, in selective study, we observed that acetaldehyde seems to be based at 9% copper doped zinc oxide as compared to the other gases like acrolein, formaldehyde, N-propanol, methanol, then acetone and methyl ketone too. Means this sensor is selectivity towards acetaldehyde for 9% of the doping, and sensor response is up to 60%. Humidity tested for that is 11% humidity is the working humidity condition for this particular sensor, and stability we have tested. Stability is up to 50 days. After sensing, we have verified the morphology of the material. That material does not lose stability. Even more, we can go for this particular sensor for sensing purpose. So these are the conclusion for this particular material. Material is a spherical shape. Response time is 60.53 seconds. Recovery time is realized 80.36 seconds, and the sensor response is 61.53%. And this sensor is working for 50 days. As a photocatalyst, we know the role of the photocatalyst, that is light energy to facilitate into the chemical reaction. That is a formation of valence band to the conduction band, that is a holes to the electron. Then reduction to the oxidation, that is we have taken one dye that's degrade with the help of the copper sulfate solution. These are the general ideas about the photocatalyst. Why we go for the photocatalyst? This is one slide, that is a cartoon is there. Initially, this probe is searching for the water. That time the level of the water in the container is very good, because he can manage by throwing the stone inside that particular container. Water is get treated because of the weight of the stone. Then further the level of the water is again go down. To take the water is not possible by throwing the stone, so he utilizes the straw to pick up the water. Then again the condition is getting worse. The straw cannot be possible again. So he put the motor and lift the water and see his thrust easily. But when the last condition comes, if there is no water, what to do? So the scientists need to think for the sustainable development, so that whatever the resources are available right now for the use drinking purpose as well as for the normal use of the water, then we have to take the water from the waste and that we have to purify it and utilize it. That we have to do. And how could it be possible? That is can be possible with the help of the nanotechnology. Nanotechnology can do anything, but the safety is another way. So we have to synthesize such a metals that can be a sustainable and that can be a edible one. Medieval is very important because if that material goes in, that cannot hazard the human body, and therefore we have done the work. That is, this is the situation right now. This is the water from where we have to collect and we have to use it. So we have fabricated some polyacrylonitrile silver graphite hybrid nanofibers we have synthesized. This is the complete process. We have the electrospinning setup. We have draw the nanofibers with help of the electrospinning in the form of the acrylonitrile polymers. Initially, we have taken the graphite hummus method. We have utilized, converted to the graphene oxide, and reduce the silver nitrate into the metal silver, and that been decorated over the surface of the graphene oxide. That is called as a silver graphene oxide nanoparticles. And further, that silver graphene oxide particles been decorated over the polyacrylonitrile nanoparticles. Okay, by the help of the electrospin. This is the exciting FDI. I will not go in detail. These are the XPS and FESM of this particular material. If you look into this, fibers are a long length. Why we call it nano fiber? The length cannot be in the form of the nano, but whatever the diameter of the fiber is there, that is in the form of the nano. And whatever the porous structure is there, porosity is there, that pores inside that particular fibers are in the size of the form of the nano. And in that particular pores, we have decorated that silver graphene oxide nanoparticles. So this is the bone-like structure. It should be it is a porous bone-like structure, and this is the photocatalytic activity for the material you have tested. Simple tan fiber shows 25% degradation. Silver graphene oxide nanoparticle shows 79% degradation, and pan silver graphene oxide hybrid nanofiber shows 88.1%. The reason is that whatever the tan is there, it is simple porous material. It doesn't have any supporting material to enhance the conduction. That is the band gap. Silver graphene oxide doesn't have that much ability to enhance the band gap. But when we decorate that silver graphene oxide over the surface of the pan, it increases the band gap. That is, the recombination can be possible easily. Then for the methyl orange, we have observed that 82%. And when we compare in both the dyes, methyl blue and methyl orange, 88.1% is not there. The reason is that because of the negative charge and the positive charge. Here, in case of methyl orange, negative charges are there, and therefore the repulsion, the proper degradation cannot be happened. Means this material is very responsive for the degradation of the methylene. Here is the silicon. This is the photocatalytic activity without catalyst. Kinetic study pseudo-unimolecular first order reaction, and this is the degradation mechanism. As I mentioned, there is a change in the band gap, increasing that particular, and recombination is being happened. The uniform reduction is being possible, and we have done the LCMS of that particular material. Only the degradation is the change in color, is not the degradation. A complete mineralization is suggesting the material is getting degraded. We have done the reusability study. We have done with the pincher also, and we done with the POC. After reusability, the XI is here, FPI is here. There is no change in the structure. We have gone up to 7 cycles. Now we are trying to go more because whatever the catalyst is available, that catalyst can be utilized more and more so that the safety purpose can be solved and the sustainability is also possible. This is the comparative study. The dye degrades in 75 minutes and 90 minutes under solar condition only. No external condition is required. One more study we have done, that is a heterogeneous catalysis with the help of the detailed metal organic framework. Here, metal organic framework, what is meant by metal? Organic linker is a blue line and circle is a metal ion. It forms a complete structure, that is a metal organic framework. advantages and disadvantages. That is the most important is the surface to the volume ratio as well as the porosity of the material. And many organic transformation reaction can be possible with the help of this. I go fast. Preparation of the nickel. This is the way we have used 4 organic linkers. PDCA benzene 1,4-dicarboxylic acid, benzene 1,3,5-dicarboxylic acid, 2,6-naphthalene dicarboxylic acid, 4,4-biphenyl dicarboxylic acid we have used. And we have named it as a NiBDCA, NiBDCA, NiMDCA, NiBPDCA. So these are the exciting things compared with that particular organic linker. Thermal stability with UV DRS and API we have done. I directly go with the surface area and core dimension. It's very important for the metal organic compound. In NiBPDCA, with the base, that is a surface area is 353 meters square per gram. Average diameter is 33.2 nanometer, and total core volume is 2.902 cm3 per gram. Therefore, BPDCA is the best organic linker for the formation of nickel metal organic compound. And these are the structures. This is the surface study. Uniform and the scattered material is observed in case of the PPCA. And we have gone with the Vignelis reaction. This Vignelis reaction is nothing but a urea or thiourea plus aldehyde with 1,3-dicarbonyl compound. They use the DHMPS. That is a Vignelic adder. And these are the biological activities of this. So if you look into this, 20 milligram of the catalyst is sufficient. Under solvent-free condition, use 89% of it as compared to the others. We have more selective. We have done the selectivity to the position. That is with the help of with the alkyl group. If you look into this, that is 3,4,5-trimethoxybenzaldehyde shows 97% yield within 30. This is the comparative study. This activity up to 5th cycle. So finally, I just say that materials can be utilized as a gas sensor for the heterogeneous catalysis as well as a photocatalyst for the degradation of the dye, for the betterment of the organic transformation reaction, and for the sensing with the selectivity study. Due to the high surface to the volume ratio and porosity, there seems to be very good degrading material for the hazardous organic dye. Material shows good reusability and impressive disability. So this is my research group from previous, that is from Jalgaon University and now from the Mumbai University. Under my guidance, senior fellow Mr. Arsola and Morankar on the industrial project, many projects from CSIR, DSP, UGC, DRDO, DRNS. I thank Student Funding Agency for providing me this funding, and special thanks to my students. Because of them, I am able to present my work in front of you, learned people. Thank you for
Thank you very much, sir, for knowledge. To talk briefly on various aspects of nano materials. My question would be, I mean, the forum is open for discussion. Before that, I would like to have a question.
So, wonderful talk on this. Graphene based material. First, that it thermograph shows nickel oxide was zinc oxide material.
yes, because of the instrument information. Because we have the instrument up to 1,000. Because we have gone last time at 1,100. The sensor is getting damaged. That's why it will stop to go more than 1,000 degrees.
One more interesting question is that we have new found this zinc oxide. You fabricated that zinc oxide material like hydrogen. So out of that, you said that
I don't
we
have
have
See, because when we talk about the co-precipitation or Soldier method, we need to provide the external device for the control temperature. Here we can control the temperature as well as we can change the morphology in case of the hydrothermal. Because changing the temperatures, variation in the temperature, we can get the good morphology by with respect to the temperature, and that's what we have done.
Any more questions, please?
So thank you, very nice lecture. One question your co-precipitation method. You can take a step and also clean a step, and you do co-precipitation. So you have the spherical particle of the oxide, very smooth surface. Why is the surface so smooth? And why are the three oxide particles side? Why are these particles?
Because initially what we have done, zinc acetate is reacted with ammonium hydroxide. Okay, it converted into the zinc hydroxide, and then we have added tin acetate after the formation. Yes.
I have one small query on. This is very general. Probably this will be very nursery type of question. So you told about that size depends on the nanoparticles. So the large surface area you are telling, is it possible to reduce the nano into pico size or femto or atto? There are so many sizes.
That can be possible when people see people doesn't actually nanotechnology is from the ancient time.
Yeah.
We don't have such tools to identify the size of the material.
Size of
Turning microscope is comes into existence and people came to know that whatever the material we have synthesized that is in the computer.
Yeah, exactly.
If the instrument comes in such a way that can understand the pico, that time we say that we can divert it to the pico.
Pico size, then femto is there, then atto is there. Atto is there.
As the need of the people goes on increasing, the technology will come into existence.
One more thing is that fabrication of your hybrid, that is patented, or you are going the fabrication pan and
no, we don't make
that cannot be patented.
No, it is not patented. It is directly published.
Okay.
Yes.
Thank
Application in composting, as you said, one of the applications regarding your nano
Composite. If the composite that is in the polymer. When we talk about the polymer, it is a composite. In case I am talking about the composite. That composite is of two types. One is the micro composite and second is the nano composite. When we add a micro composite, that is a dispersive phase and a continuous phase. Polymer is a continuous phase and nano material is a dispersive phase. When we add anything into the polymer, that enhances the property. That is the composite. That is the two phase.
I request Aarti Shanware Madam to felicitate Professor Shimpi Sir by offering memento and certificate. Thank you, ma'am. Thank you, sir.
So third lecturing session. Speaker is Dr. Ratiram Gomaji Chaudhary. Actually, Chaudhary sir needs no introduction. Well-known researcher from our region and internationally acclaimed, I can say. He's presently working as an associate professor and head in postgraduate department of chemistry, SK Porwal College, Kampi. He is Senate member of RTM Nagpur University, Nagpur. He is Board of Studies member of chemistry and also worked as task force member and several committees of RTM in Nagpur University. Recently, he has received Best Researcher Award 2023 by RTMNU and SK Porwal College Kamti, an international conference on functional materials jointly organized by Nabira Mahavidyalaya Kato. His research areas of interest are biogenic synthesis, graphene-based nanohybrids, microbial assay, and photocatalysis. He has completed one major research project funded by SERP DST. He is recognized supervisor and produced 6 PhDs till now, while 7 are undergoing and completed 65 MSc projects. Moreover, he is recipient of JRF granted by UGC, Outstanding Reviewer Award by IOP Publisher, and many more. Moreover, he is recipient. He has published 6 books, 26 book chapters, and 151 articles in SCI Scopus indexing journals, having citations 2298 with H index is 28, very commendable indeed. He is reviewer of 71 SCI Scopus journals. He worked as a guest editor of Elsewhere, Bentham Science, and delivered several invited lectures, resource talks, and acted as a chairperson in various international events held in Sweden, Finland, Nepal, Argentina, Delhi, Allahabad, West Bengal, Dur, Uttarakhand, Kerala, etc. So, warm welcome to you, sir. Now, what are you for your questions?
Thank you, madam. Thank you so much for my introduction. Ladies and gentlemen, thank you so much, Community College and Navy, and as well as Greater Noida for giving me opportunity to deliver my talk. Since early in the morning, since 9:30, everybody are speaking on the green synthesis, biosynthesis, sustainability. So what is the sustainability? So whole world, all over the globe, are going and offering green synthesis, and biosynthesis, biogenic synthesis, bio-inspired synthesis. So what is that? And main thing is that the sustainability, what will happen, once you synthesize the material. So that thing is the sustainability. So as the conference on the advanced sustainable futuristic material, so I thought that I should give the talk on the biogenic synthesis and biofabrication. So, ladies and gentlemen, I'd like to talk on the my theme of talk is on totally the biogenic synthesis. So I must acknowledge my college because my college provided a huge grant for the research. So therefore, every 5 years, college organized international conference with the different institute. In 2015, it was organized with Danforth. In 2019, it was organized with ISCAS. In 2020 and 21, it was organized with the private college. And further, in 2022, it was organized with the SPMS, Society for Promotion of Material Science. And every year we are organizing state level competition for the youth student. As you told you that the biogenic synthesis, ladies and gentlemen, we must offer us toward the biogenic synthesis. Biogenic synthesis is eco-friendly and cheap. There is none of the cost effective because every man, every human, every researcher, every scientist are going toward the fabrication. In my synthesis, in my work, I am taking only salt, and there is none of precursor from conventional technique, conventional chemical. I am taking the precursor, stabilizing agent, capping agent, and the seeding agent from the plants and other biological. So these are the examples of the nanoscale material. As earlier, the talk delivered by synthesis, it was nice on the nanoparticle, and keynote address given by the Adhikari sir on zinc oxide and copper oxide. since early in the morning, people are talking on the nanoparticle, nanocomposite, quantum dots, graphite carbon nitride. So these are the best examples. Best example is our DNA and RNA and quantum dots, nano dots, then 16, single wall, multiple wall. So these are the examples of the nanoparticle, nanoscale material. So I could not emphasize on the bottom up approach and the top down approach. So it is well known techniques. The bottom up approach, so top down bottoms, top to bottoms, the physics people, material people are using, and however the chemical people, bottom up approach, that atom to the nanoparticle. So there are several methods, several techniques can be used to utilize to fabrication the nanoscale material. Next. And these nanoscale materials, how they use can be synthesized by several conventional techniques, but it have a number of the couple of shifts. You know that you are the witness. You can in the synthesis of nanomaterial by conventional method. You must have SDS. Surfactant is the main role for the synthesis of nanomaterial unless and until surfactant you could not get the material nano. Other people are quality people synthesize nanomaterial. So SDS is most important. Sodium glucose sulfate. Then CTAF, cetyl trimethyl butyl ammonium. Cetyl trimethyl ammonium, that is hydroxide, another ammonium phosphate. So these are the important. So it has some drawbacks with conventional technique, like the large electric power utilization require more much energy. So you must think of the energy, electric energy. Then next, expensive reagents are solvent. In the conventional technique, like SDS, CTAB, that is quaternary salt, these are the acting as the surfactant, capping agent, stabilizing agent. Then solvents are also very high. Then use of the excessive chemicals, this is also cancerogenic, carcinogenic. Okay, so in my biology, I did not take very extra only water and none of taking the solvents. So third, involvement of the toxic chemicals. Surfactant are difficult to remove. That is most important thing is that to remove this surfactant is very task, very difficult. But sometimes in your material it gives impurity because of this surfactant. Then next, very complicated methods. These methods are very complicated. Sometimes not getting the yields. It is also very much less. Then use of expensive equipment require the use expensive more than 2 lakh or 5 lakh or 25 lakh instrumentation for the synthesis of nanomaterial. In foreign people, Western people, and American people using the expensive equipment that is more than 25 lakhs. It will be crore. Next. And these are the drawbacks. These are the drawbacks of the conventional technique. You might have heard that dizziness, science, it give you, and sometimes this is the headache, nausea when you are working. When you are working, when you are synthesizing material, you could not get such thing. But after 60 or when at the age of 60 or 55, it will be realized. So, and if you give the long-term health hazards, so lung damage, liver, kidney damage, central nervous system. You might be assisted with this. This is after 55, after 50. Next. So these are the toxic chemicals. So what we do? So we must demolish this phytochemical, use of the toxic chemical. So you must use bacteria mediated, plant mediated, then algae mediated, DNA mediated, RNA mediated, and these are the biogenic chemicals. Next. So why should we do? As I told earlier that these are the toxic, these are the not human being friendly, eco friendly. So why we should the biogenic synthesis? Why should go with the biogenic? Why should go with the eco friendly? So why? So this is a cheaper. Supposed to be your taken if you synthesize the nanomaterial using plant mediated. No requirement of the money. Then use of the non-hazardous biochemicals. You not to take any types of conventional chemicals. So all the chemicals that is called as phytochemicals already in the plant, yeah, algae, yeah, fungi. Then we need to handle simple. There is no any precautions. The next harmless to the approach, there is harmless approach. Next, straightforward, faster, and incredible properties. There is the most important thing as incredible properties. Because of the assessment during the fabrication of the nanoparticle, there is the assessment of the biomolecules, lipids, proteins, DNA, RNA, or phytochemicals that give the scaffold structure, that give the scaffold material, and that scaffold material give the enhanced property in the degradation of the dye, degradation of pharmaceutical drug, yeah, pesticide, yeah, biological assay, yeah, cancer activity, whatever that. Next. These are the plants. So you can use the biosynthesis of nanomaterial by using the different plants of that is maybe flowers, stem, then roots, plumule. So this kind you can use the as the stabilizing protecting as a surfactant as the phytochemicals from derived from the plants. Next, these are the, as I told earlier, that these phytochemicals acting as the role that is called as surfactant, that is called as stabilizing agent, that is called as protective agent, that is called as shielding agent. So all these roles will be performed by this phytochemical. That phytochemical may be secondary metabolites. The secondary metabolites is more important. There may be terpenoids, stannine, various thousands of chemicals are there. But out of that thousands chemicals, that chemicals are not important. Only few chemicals are present in the plants. It will be important. And how will you recognize? Whenever there is a field work, so at that time to recognize the plant, I could not recognize the plant. So botanist, that is called a taxonomist. So taxonomy will identify the plant. So whenever there is a field work, so I am always with Dr. Subhash Kumar, he is a taxonomist, because I could not find any plant. So identification of plant, there is requirement of the taxonomist. So these are the phytochemicals that we useful for the fabrication of the nanomaterial. Next. So already I spoke. Next. So these are the, if you find in the literature of review, you know, found lakhs of the nanomaterial. It may be nanoparticle, nanocomposite, quantum dots, several nanomaterial are synthesized by the biochemicals, yeah, phytochemicals. Yeah, and most of the peoples, China people started biological synthesis. Then Japan people, and then India. Then some Indonesia, Thailand, like that. Because last year in 2020, when I have a talk in Argentina, the people are miracles. How it is possible that material is synthesized from plant? Most of the questions arise from the student. They are sometimes, some people laugh. How it is possible? So, Baba, there is a, because after synthesis we have experience, ideas, exciting, same, and that gives the confirmation. And nowadays it is a popular technique. So the literature you will find the tremendous literature. Find the algae meditate, fungi meditate, and microbe meditate, DNA meditate, RNA meditate, and plant meditate is the best, because in plant meditate it is very simple, easy, straightforward. And if you find the silver, and if you are one or two do the biosynthesis, the silver is the best. Every plant you will get the silver. I don't know why. I don't know. But it is not it is, and you don't think that it is supposed to be pick out the plant and you will get nanoparticle. No. Okay, it requires you must study the what type of particle present in the plant. Okay, so every plant doesn't give the material, nanomaterial, you have synthesis of zinc oxide, nickel oxide, carbon oxide, titanium, whatever that. Okay, so but silver will give the nanoparticle, and silver is most of the people are synthesized silver and gold. Next, these are the nanomaterial it is synthesized in my laboratory using the surfactant. It is a conventional technique, material synthesized by using some surfactant. Next, and this work is already published, so I will not emphasize on this. Next, this work is not yet published, but the material we have synthesized without surfactant. It is very difficult to synthesize material because earlier I spoke that to synthesize nanomaterial it requires surfactant. And this is the material we are synthesized using without surfactant. So next, and most important thing is that synthesized material using surfactant, yeah, none of surfactant, but with whole formation. So whole formation very big. Because when whole formation is called whole material, that very fantastic and excellent material. Why? Because it uses outer surface as well as inner surface. It is both surface you are using. However, supposed to be one of the materials in the nanosphere. So we will use only outer sphere. Inner sphere will not use. But if the material is whole formatted, so it will use outer space as well as inner space, and you will give the maximum. So because of outer and inner space. Next, there are some nanomaterial and already published in various journals, and this material is synthesized in my laboratory by my very students. So next, and this is the paper having cited by many papers. Right now, we have 140 citation in 3 years. 4 years. It was published in 2019, 1930. And this is the first paper which was published on biogenic synthesis. In this paper, I have taken I have synthesized the copper oxide nanoparticle using the Bonalysis and Phylanthus reticulus. This material, first of all, I have prepared the plant extract, and copper nitrate. I have taken the copper nitrate 2.41 gram, and then it's just stored for half an hour. After half an hour, you will get the color is changed, and after 2 years, you will get different color. The different color because of the formation of the hydroxide molecule. Sometimes there is a chelation. You never think that. You never ever think that you will get direct copper oxide. Before metal oxide, you will get some chelation. It forms some chelate compound. And how we say what is the proof? And you are saying that. So there is a proof because after TGA formation, the material last at 700, and there is the attachment of some moiety because we are synthesizing copper oxide. So you must give the peak of copper oxide, but instead of copper oxide, there is an attachment of several moiety, organic moiety. So who's come from? Where did it come from? So it came from the plant extract. And after calcine, the material was anile and the safe was this microsphere. And next, and it was confirmed by FTR spectroscopy, XPS, EDS, SAM, TEM. As for the XRD, the peak obtained at 40 to 30, 35 to 40, the XRD. Then the crystallite size was obtained 5 nanometer, and its phase is monoclinic. And so after monoclinic and getting, then it was Raman spectroscopy, then as well as FTR, then EDS. After EDS, we did carry out the XPS. So next, XPS is most important to EDS and XPS. So after EDS, you do not do the XPS, but supposed to be find out the chemical composition and chemical state +1 +2. So it will give the exact oxygen state. So in copper, if you got the peak at 943 and 963, so there is a satellite peak. So that indicates you will get the +2 oxygen. So that indicates So to confirm the chemical state, you must check out the XPS. But XPS is precious technique as well as costly. It requires more than 4 to 5,000 per person. Next. Next. And it is scaffold morphology. As I told earlier, the plant mediated, to plant mediated give the scaffold morphology. Both the sugar will be here. So because of what? So scaffold morphology will give it may be due to the plant mediated, it may be due to the calcination at high level calcination, it may be due to the constant stirring, it may be due to the prolonged heating. So these are the 4 reasons to give the scaffold structure. So here the material is actually this is the microsphere. The scale reveal that the material synthesized microsphere. But each microsphere, if you see from this scenario, if you see the image that each microsphere constituted by several couple of nanosphere. Okay. The next, and this is the stem. So they reveal the nanoparticle size, the whatever the material size is the nanoparticle level and nano level. Next. Then monodisperse, as you see in the image of same image, where the microsphere in homogeneous, that is isotropic, that is called as, it means all microsphere nearly same size, that is called isotropic, homogeneous size. So as the homogeneous shape bed as well as AFM studies, those AFM graph is shows that there is a single graph and as well as some minute peak is there. So minute peak, so that indicate that, that's why I say that nearly, if not purely homogenized. If it is purely homogenized, whole microsphere shape and structure are same. So that A can reveal that is nearly homogenized, and this base surface conveys the base surface reveal that mesoporous nature, and as well as why mesoporous nature, because 34 nanometer as well as 42 nanometer, and surface area is also good. Surface area is 22 meter square per gram. Next, and likewise, like the copper oxide, I have couple of materials synthesized by using the plant extract. It may be flower extract, it may be leaves extract, it may be root extract. So one of the paper after copper oxide, we were successfully synthesized the Bi2O3 nanoparticle using the trinomial flower, and it was confirmed by the various analytical techniques, XPS, JM, FTR, etc. like that. Next, and it is already published in the ASS Omega factor 4.1. Next, similarly, nickel oxide also fabricated using the plant extract, and that material were used for the Bombay cell line, where Bombay cell line that is still, and it that practical that we are performing the zoology lab, that is by Professor M.M. Rice and Dr. Alok Rice was there, and further as well as is nickel oxide were tested for the liver cell of Rohitha, and it indicated that in last slide there is a gap between the cells, that is called as parenchyma. It is cells are separated, and also it is published in the SS Omega. Next, similarly, this is the work which is unpublished, recently reviewed, received for the minor revision in chemosphere. Chemosphere is one of the reputed journal. 2 to 3 papers I rejected earlier, and this paper is under revision, and we are able to synthesize this copper amalgamated material by using the flower extract of the Catharanthus roses. So I could not go in details because it is not published. Next, and these are the several papers were synthesized by various using the bio-inspired material, like the Janus cerium group, bismuth oxide. After before publication, this work was patented with IIT Bombay. That is Arnab Datta, and one of my students again was there. And next, the phytochemical. Similarly, zinc oxide, graphene dope zinc oxide were synthesized using Sylvania with Bipinosa. Then Solani assisted microsynthesis. Dr. Sudip Mondal there. Sudip Mondal synthesized this work in the laboratory of microbiology and received more than 70 citations in 2 years. So, and similarly, just the data is only the medicated platinum work was patent. It was not yet published, but since 1 month it will be published soon in next week. So, and we have successfully synthesized this platinum material by using this. It is not a plant, this is algae. So, algae mediated nanomaterial. Next. And after this fabrication, after the fully successful fabrication of the material, we were evaluated their antioxidant activity, and antimicrobial activity, cancerous activity, then microbial activity, then degradation, pharmaceutical drug degradation. There are so many, as well as water splitting, that is oxygen and hydrogen evaluation. So here we found out that here methanolic solution as compared to ethanol solution, the methanolic solution give the highest the antioxidant activity, and it was found that the plant mediated material as compared to the nanoparticle it give the highest antioxidant. Next. Then before the any microbial activity or biomedical application, with the help of docking, computational analysis, we were studied. Dr. Kaniya Dadur is there, my friend at JB Science Varda. So before analysis of antimicrobial and anti-cancer activity, so we studied with docking, and the material was coated with the antimicrobial by getting the 0.2 to 3 docking, minus 2 to 3 docking energy. Next. Then similarly, antioxidant, antibacterial activity, where copper oxide, zinc oxide, nickel oxide, so were performed for the antibacterial activity, and it shown that synthesized as compared to conventional nanomaterial, the biosynthesized nanomaterial were shown the highest zone of innovation. So because of the scarp mighty. Next. And similarly, as you told me earlier, the material were assessed by the Mumbai cell line. You will find that the study at 10 microgram at 5 minutes, 20 minutes, 30 minutes, 50 minutes. So there will the cracking, and that is lethal effect, the breaking of the cell. So there is a lethal effect shown, and if you see the at 60 minutes, totally cells are cracked. That means cells are damaged. And if you find the next, if the concentration is increased, next, if you will find here, once the concentration is increased, the cell is totally damaged. So totally, it means you show the lethal effect is totally increased high. So here the cells were treated with the 50 microgram per ml, and it was shown that within a second that totally cells are, it means dead of the cell. So next. So this is the plausible mechanism. So this is the plausible mechanism of our thinking. It is not, we are not taking any publication. This is so that microsphere and nanosphere, one shot in the endocytosis, and it will endoplasm, reticulosome, mitochondria, whatever that is damaged, and there is a formation of vacuole because of pressure. And once the vacuoles are increased, so obviously it will the bombardment of the cells, and it will do endocytosis. So next. And similarly, this work is from the earlier copper aluminate, that is chemistry, is under revision. So we have also seen that here as killing rate at a particular time, So it was found that it means here that 20 micrographs, we are taking the 10 microgram, 10 to microgram, 10 to microgram, 30 micrograms, 40 microgram, 50 microgram. So out of that 20 microgram, the most of the pathogen, you find that at 20 micrograms, that is, my cells are totally, with both of the pathogens are totally seized. This is the green graph reveal that it is the growth of the pathogen, that is control. And once the given the dose of the nanomaterial copper aluminated, so that the growth of the pathogen is totally decline and decrease. Okay, so this is the toxicity of the nanomaterial and nanocomposites. Next. Similarly, we were also material we are tested for the dye degradation. We are taking the CR dye, and this is what published in this is omega. In this where do the material this indicate that this this indicates the dye degradation. And earlier the talk given by the synthesis said that there is a degradation is it should be, it means that radical formation single and the color symbol changes of color to the non, it means pure white. It is not indicated with the degradation. It should degrade of the radicals. That materials it should be totally different. Okay, so here we successful to find out the degradation of dye using these BIOT materials. Next, and these are the few publications in association with Professor NBC sir, Adhikari sir. There are recently this bio-inspired government-based material production and designs for the photocatalytic and electrochemical performance were published in RSA nanoscale advances in the with the scientific contribution of Professor Adhikari sir, Swami and Abdullah, IIT peoples and my students. And there are several review papers there which were written with the association of the several researchers of different countries. And these books, Emerging Nanomaterial and Their Impact Factor, is very good book. It was written with the help and the as well as and with the I can say blessing of the NBC sir. NBC sir is sitting here, so it's the blessing because every early morning he calls me. So really, and earlier this first book it was written with Professor Alok and Devendra Pratap Singh. Next, and so this is my conclusion. So in conclusion, biosynthesized material are very cheap, and everybody can synthesize the material using the bio-inspired. It means it may be plant, maybe algae, it may be microbes, it may be RNA, it may be DNA, it may be it may be biolipids, proteins, and it may be plant mediated, so like that. And as a synthesized material, it can be useful in various activities, might be antibacterial, antifungal, and uh, different anti-cancer, as well as dye degradation of various dyes, pharmaceutical or pesticide, like that. So next, and with the support of this would be possible with the support of ACRB. The ACRB funded. So it was the project was funded in 2015, and it was possible because of ACRB funding. And second most important thing is that it was possible because of the characterization. It was done, carried out several instrumentation, several institute, IIT Bombay, Kochi, then Chandigarh, and VNIT, ERI, as well as postgraduate department of physics, chemistry, Satyabama University for AFM of next. And further, this is most important thing is that because early in the morning, the session that lab science was said that the collaboration is most important. Unless and until collaboration would not get growth. because single man can do all those things. So collaboration is most important. So because of the collaboration, because of the blessing, because of the support, because of the assistancy, so these peoples are the responsible. These people, so backbones, we must say the backbones. So, and because of these people, I synthesize material, fabricate materials, and it means regular article, review article, chapter, and books. So I must thank you so much, my Junera sir, Singh sir, Adhikari sir, Professor Sami von Jordan, Professor Martin from Argentina, Professor Abdullah from Texas University, then uh, then Nitin Mishram from his my colleague, Zoology Department, then Dr. Lambert from Devri, then Dr. Aniruddha Mundal is my student and working as a postdoc in Sweden. Uh, then Dr. Subhash Sankanar, the role of Subhash Sankanar is too much. Then Dr. Ashish Tiblen, Dr. Kanaya Dadure for talking, and that Rohit Sharma from PH University. So thank you so much. Thank you so much, sir. Thank you so much, each and everybody for patience by hearing to me and as well as thank you so much, Dr. Gunule sir, Badnaik sir, and the whole committee members, technical steering member, as well as the chairperson. And thank you so much.
Thank you, Rapiram. If you have any quick questions, you can please. Shardul, please.
Thank you so much for enlightening us with this such an explorative work. And even when there is not a answer available, we can use for the same. One question which I wonder, this is nickel oxide carbon. You studied against Bombay's Morris and that has proven that it showed the toxicity. However, what was the basic objective behind that?
Yes, good question. Same thing. Once we got the good result. So Dr. N.M. said that, Rathiram, it may be due to the DMSO because there is a solvent. The question is raised by it was good. It may be due to the DMSO. It may be, yes, the 100% it is result because of nickel oxide. But no doubt. After that, we also perform the DMSO. After that, we also perform that test by DMSO. We did not get. So we comparatively same thing of platinum to nickel platinum material for anti-cancer activity, which was performed at Ambedkar College, Dr. Dongre sir. So the activity was very awesome. So he said that, so it is not possible. It is actually high. It is I think breast cancer, breast same for so we did that second time also good. Then third time it is also good. And as well as we have performed the solvent as well as so it means we are doing the analysis material as well as whatever solvent we are comparing. Similarly, right now the Tiple had done the work on the insect. So but the result was good. So he said that result was good. Then I asked, did you taken the result by using the solvent? No. Then again we have taken. So they are doing sir.
Okay, thank you, Dr. Rathiram. Because actually we are running short of time. So now, yeah, of course, excellent presentation. Your publication also shows that your work. So once again, big round of applause for all the three speakers. Now the organizer, please.
I request Principal Badwai to present memento and certificate to felicitate our respected invited talk, Professor Chaudhary sir. Shortly we are starting oral presentation. Those I am going to announce the name. Those who are present, please bring your presentations in pen drive just now. Abdul Rahim, Aishwarya Umate, Akshay Amit Borkar, Amrapali Patil, Anushka Punde, अर्चना पटले, अर्चना कांटे, आरती हडप, अरुण कुमार बांगर, अरविंद